Okay, so before we get started with our last part of our capacitance and electric potential, very long unit on those two topics, I want to address a question that we had yesterday. Who asked the question? It was Alex, right? The question, which one was it? Number 20. So the question says, if the charge on a capacitor is doubled, so we're going to go from Q to 2Q, the energy stored is, we want to see what happens to the energy on the capacitor. Okay. And you would think, by the equation, energy stored in a capacitor is equal to 1/2 Q delta V, that if you double the charge, you get double the stored energy, correct? But that is flawed. That is flawed. And let me show you why it's flawed. I'm going to pull up my trusty capacitor lab. This is actually a different one because the one that you did didn't have dielectrics on it. Here I go. Let me move this guy out of the way.
Which number is this?
21. So let's say I put a certain amount of charge on it with the battery. Okay. I've stored, let's say I store 0.7 times 10 to the negative 13th. So that would be 7 nanocoulombs of charge. Right. And I use the battery to do so, right? If I want to put more charge on the battery, what must I do?
More charge on the battery?
If I want to put more charge on the capacitor, I said, if I want more charge on the capacitor, what do I need to do?
Up the voltage.
Up the voltage on the battery, which will cause the voltage across the capacitor plates to also increase. So if I use the battery, which will be at the same potential as the capacitor, to increase the charge, then I must necessarily increase the voltage as well. So I can't just double the charge on a capacitor without actually doubling the voltage, because the capacitance is equal to charge over potential difference. The capacitance does not change. So if I increase the charge, then I must increase. If I increase the charge, I must increase the potential difference by the same amount, right? Because I know that the capacitance won't change.
Well, isn't it also that delta V, it's like electric field times the displacement, so it's really just KQ over R. So you're going to end up having two Q's in there, so it'll just be Q squared.
Yeah, and you can something easier than that. You're thinking along the right lines, but using equations that are explicitly written on our equation sheet. I don't know why I erased that. I still need that. I know that capacitance is charge per delta V, and actually it's written on the formula sheet as potential difference across a capacitor plate equals Q over the capacitance. The definition of capacitance is Q over delta V. And so I can just plug this in for delta V here, right? And when I do that, I get 1/2 Q times Q over delta V, which, like you pointed out, gives me Q over C. Ooh, not starting off great today. Which, as you pointed out, is Q going to end up being Q squared over 2C. So that's another equation that they didn't decide to put on your equation sheet for the energy stored in the capacitor. Right? You can write the energy stored in a capacitor in terms of charge and potential difference. You can also write the energy stored in a capacitor in terms of charge and capacitance by combining the relevant equations. And then on the formula sheet, it gives you the other one. This is the one that it gives you. So there's 3 general equations for the stored energy in a capacitor. but they don't give you this one because that's the call cord for you. All right, this you can derive by just solving this equation for Q. Right? So using the definition of capacitance and the general equation, or this most basic equation for stored energy, we can generate the other two, one of which is given to you on the formula sheet. Cool beans? All right. And then obviously if you write it this way, if I double the charge, then I obviously will have quadrupled the stored energy.
Beans with capacitance.
Beans with capacitance. All right.
If you were for an electric thing charged with being, what would be its capacitance compared to the larger being?
I asked Trenton, he knows. Okay, so we're going to talk about dielectrics. We're going from the realm of theoretical capacitors to actual ones that are useful, ones that we can have very direct control over the properties of, not just by varying the area or the distance, but by inserting what are called dielectrics. To understand how a dielectric operates, we have to do this old experiment where I charge the balloon and then I stick the balloon to the wall and it stays there. Right? Or like my very original idea that I came up with, obviously, I charge the balloon on my hair, the balloon sticks, charge the balloon on my hair, and then I'm not even going to do it because that's lame. I'll do it next year whenever you're not in my class. And claim it as my own.
Whenever we can talk about taking
What's that?
Who says I'm not going to be in your class next year?
Well, I hope not. Okay, so understanding how that works tells you why capacitors or dielectrics work in capacitors and how they can be used to increase the capacitance of a capacitor. You got to understand how this works, though. Okay. So before I dive into that a little more, I just want to give you the definition of a dielectric. What's that? No, not yet. Not yet. That'll be in a couple weeks. That'll be the last third of the class will be magnetism and we don't really get into electromagnetic radiation so much, but we do get all of Maxwell's equations, and then you will learn in college how to expand on Maxwell's equations to describe electromagnetic radiation or light. Yeah.
Are we going to have a mock exam with you?
Yeah. We're a little short on time, so yeah, I really want to. But yeah, we're a little behind where I want to be at this point, so stop asking questions and just listen. I'm just kidding. Okay, so a dielectric is a material in which the electric dipoles, hopefully you've seen that word before, can be induced. Dielectrics must be insulators because you can't form electric dipoles in conductors because the charge would just flow until it was no longer a dipole. And they're placed in between. Can I spell between? In between capacitor plates. I have seen problems where you fill the space between a spherical capacitor and its spherical shell with a dielectric, and it works the same way. Okay. So what does it mean to induce a dipole? Let's say I have an atom that I can consider to be spherical, a neutral atom. I don't want to do that color. Let's say I have a neutral atom that is spherical. Atoms themselves aren't spherical, because the electrons are constantly zipping around and in different plots. But overall, statistically, the electron is going to be, if this is one s orbital, or an s orbital, it's going to be all over the place. And I can model that atom as a sphere.
On average, an atom is a sphere
on average. Yes. And then I subject that atom to an external electric field. Now, if I have an electric field in this configuration, I know that I have a net positive charge down here and a negative charge up there. Right? Electric fields point from positive to negative. So what happens to this atom is that the electrons will tend to spend more of their time on the bottom part of the atom because they're feeling attracted this way. They want to go against the electric field. And so the shape of the atom, which isn't defined by the nucleus, right? The shape of the atom is defined by the electron cloud. This atom will start to resemble this kind of a shape, right? Where the electrons, since they're spending more time down here, I get an electric dipole, right? It's kind of like a water molecule. You learn about water molecules, the electric dipoles. One side is slightly positively charged, one side is slightly negatively charged because of the bent shape. So I will get, because the electrons are spending more time down here, I'll get a net negative charge down there and a net positive charge up there. Overall, it's still neutral, just like a water molecule is overall neutral. But I have now forced this atom to become an electric dipole just by subjecting it to an external electric field. Make sense? And we can see, and this is the point. This is the whole idea behind dielectrics. And again, you charge a balloon and it sticks to the wall. The wall's neutral, but I can still get electric forces into the wall, or from the wall onto the balloon, by inducing an electric dipole. There's a very complicated, robust, rigorous simulation here where I take my balloon and I rub it on the sweater and I build up net negative charge, and when I move it towards the wall, the negative charges on the surface move away, leaving a net positive charge on the surface, so I get an attractive force between the balloon. So I get an attractive force between the balloon and the wall. And if I let go of it, it gets attracted.
And now the sweater has literally 0 electrons.
Yes,
Absolutely.
yes. So this sweater is about to get zapped for sure. Okay. So now again, the electrons don't just move, right? Because electrons within atoms move incredibly fast, and really they don't move according to quantum mechanics in the way that we assume things move. They just pop in and out of existence at separate spots within the atom, insofar as quantum mechanics tells us. They just spend most of their time farther away from the surface of the wall. And so that you get that induced electric dipole. Make sense? Okay.
I found a research article, electrical capacitance of gene group systems and tissue density.
Of course you did.
It's like an academic article too. Like it has a whole abstract and everything.
Hey, just because an article is academic, that's probably pretty interesting or pretty robust. Just because an article is academic does not imply that it's
a reliable source then.
It's
This is going to be
true.
career. He's just going to write articles.
Capacitance offers a robust and non-destructive method of group method.
For the curious people of the internet.
Okay, so let's take our capacitors that we've been dealing with thus far. And we are again going to assume that the area is much, much bigger than the separation distance, so the electric field is constant. Say the separation distance d, and I charge the capacitor, and then I disconnect it. So I'm going to charge it, and then I disconnect it from the battery. Okay, so let me make a note there. Once it's charged, it is disconnected from battery. Can I spell disconnect? Disconnected from battery. Once it's charged. And then, so I have obviously established an electric field pointing from the positive plate to the negative plate. Future electrical engineers in here, you do have to deal with what happens at the edges. You get what are called edge effects, but essentially it just kind of does that. But you do have to take that into account when you're dealing with very sensitive electronics.
You can't say any mean things to it.
No, it's very sensitive. Yeah.
That's
So this I can say is positive charge density sigma on the positive plate, and then I will have negative charge density of the same magnitude on the bottom plate. And then I have an electric field established between the plates, electric field E. But then I'm going to throw an insulator in there. I'm going to take a dielectric, piece of glass, piece of polyethylene, piece of rubber, piece of paper, something, and I'm going to slide it in there in between the two capacitor plates. And so now between these two conducting capacitor plates, I have a dielectric. Again, what's a dielectric? It's just an insulator. That's it. It's just an insulator that you put between capacitor plates. That's it. But what happens is because now the same thing that I described with the atom happens. I have a bunch of atoms that are locked into place and the electrons can't flow, but they can spend more of their time where they're happier, right? As dictated by the electric field. So an atom here has electrons that are going to spend more of their time towards the top than they are the bottom, right? And that's going to happen within the entire dielectric. And what that and the best way to visualize this is just a way to visualize it, but just understand that it happens within the entire material. I can visualize this by saying, well, then I get a net negative charge on the top of the dielectric because the electrons, again, are trying to go along the electric field. They're not going to actually flow, but they're just going to kind of move and spend more of their time at the top part of the atom. And so I get a net positive charge down here at the bottom. Okay. Well, now I have this external field caused by these positive charges, these negative charges. Now I'm going to get an induced electric field within the dielectric, right? Just by putting the dielectric in there, now I'm going to get an electric field that's going to point from the bottom to the top, right? Does that make sense? Now, again, this happens within the entire dielectric, so you have each layer of atoms is going to have a net negative and a net positive charges arranged, negative on top, positive on bottom. But overall, what that means is that on the top layer of the dielectric, it's going to be net negative charge, and on the bottom layer, it's going to be net positive. So I will get an electric field that points up in this picture, in this diagram. So what I've done, I've essentially taken the top layer of this dielectric and created a negative charge density, which we call negative negative sigma, with IND for induced. I've induced a charge density at the top of the dielectric. And similarly, I've induced a positive charge density at the bottom. And those charge densities create an induced electric field within the dielectric. What's that? Ein. Yes. Simba. Positive Simba, negative Simba. Now I have the song in my head.
Now I'm thinking about is the video of the monkey looking up, but he just tosses it.
Like invert the colors on the video.
All the animals start cheering.
Did you guys see the live action remake?
No.
It's terrible. My wife had to see it, and it took all the magic. I'm not a huge Disney fan, but those movies are pretty good. It's terrible. It's terrible. That's just my opinion. Okay.
I'll sue you for it.
So.
You're not a financial advisor and have not financial advice.
Yeah. Okay, so it turns out that the more charge density you put on the plates, the more induced charge density we get. That should be pretty obvious that would happen, right? And it can be shown that the induced charge density is directly proportional to the charge density on the actual plates. The charge density that I induce within the top and bottom layers of the dielectric is proportional to the charge density of the plates themselves. And so I can write a nice expression with a proportionality constant to relate those two. Let's call it B. The thing is that the induced charge density is always going to be less than. If it was greater than, there would be implications there that would violate the law of conservation of energy. So just understand that, and so if the induced charge density within the dielectric is always less than the actual charge density on the capacitor plates, then that implies that this proportionality constant must be less than 1, right? And then you want to remember that the electric field is sigma over epsilon naught for a parallel plate capacitor with air or vacuum between the plates. That's the equation. So it's directly proportional to charge density. So if I have induced this electric field inside, that E induced will be equal to the induced sigma, the induced charge density over epsilon naught. Right? You following me so far?
Yeah.
And what if I want to know, because now I have a total electric field. I don't have, like, you don't see field lines from one and then field lines from another. You see the net electric field that results from the two fields interacting. And so to figure out the total electric field, and I'm going to be careful with my vector symbols in this expression here because I got vectors, I got field vectors pointing in opposite directions I need to combine. So the total electric field is going to be the electric field generated by the capacitor plates plus the electric field induced within the dielectric, again, because they exist within the same space. And so that total electric field then is going to be, well, if I define, down as positive here, if I consider the external electric field from the capacitor plates to be positive, well, it's going to be E minus E induced. Right? The E induced, they're going to fight each other. They're going to fight each other. One's pointing in one direction, one's pointing in the other direction. That's the principle of superposition at work. But I know that E induced, I know that the induced electric field is proportional to, I didn't finish this off. Timothy, you're supposed to remind me. Jeez. Sigma induced is equal to B times sigma, right? It's direct proportion there. And so I can write this as B times sigma over epsilon naught. Sigma over epsilon naught is the original electric field. So the induced electric field is simply B times the original electric field. I knew I was missing something. But that makes sense, right? That just follows directly.
Yeah.
If the electric field is directly proportional to charge density, and the induced charge density is directly proportional to the original charge density by this factor, then the electric field should be affected by that same factor. So I can rewrite this expression to get the total electric field as electric field minus this proportionality constant B times the electric field. And those electric fields are the same. Those are the expressions for the original electric field, right? B times the original electric field is the induced electric field. So I know the total electric field is equal to the electric field times 1 minus that proportionality constant B. And now, for reasons that just make the math work out easier, 1 minus B isn't something we typically use. It just makes the equations, as you'll see in a minute, makes the equations a little easier to deal with. We define this quantity kappa, which is a weird looking K. It's a Greek letter K.
It's also twitchy.
What is it?
It's also twitchy.
Cool. I don't know what that means. I'm not cool at all. And so we define kappa in terms of this proportion, because we know 1 minus B is a constant, right? We want just a single letter. And so we define kappa as not 1 minus B, but 1 over 1 minus B. And there's reasons for that. It just makes the math work out to be a little easier. Okay. And if B is less than 1, then kappa must be what? It must be greater than 1. Unless it's air, because B for air is 0, right? And then not 0, it's 1. B is 1 for air or vacuum because the induced charge density is just the same. No, it's 0. What am I talking about?
Yeah.
There's 0 induced charge density if you have no dielectric, and so B must be 0, and so kappa is 1. Right?
Exactly, Mr. Dillon.
Yeah, I know what I'm talking about, really. All right. So what that means is I can rewrite my electric field equation here. The total electric field within a capacitor with a dielectric is going to be that this is the total electric field due to both the capacitor plates that are charged and the induced field within the dielectric material, as not E times kappa, but E over kappa. And that tells me that the total electric field, by inserting the dielectric, actually reduces gets reduced from the original electric field with no dielectric.
I don't know why they had to make it kappa, because if they just make it capital K, it's still different than Coulomb's.
Yeah, I don't know. That's Joel. He came up with the idea.
Joel, you're stupid.
Hey.
Apparently it's also a type of car.
Huh?
Apparently kappa is also a type of car.
Tied with a what?
Car. C-A-R. Automobile.
I don't know what you're talking about. Okay. So what that means is that I reduce the electric field within a capacitor just by putting in a dielectric. Yeah, I've reduced the total electric field. And we have a nice expression that relates the voltage across a capacitor to the electric field within the capacitor. Technically, if I'm going from positive to negative, then it's a negative there. No, if I go from negative to positive, then it would be negative ED. But the magnitude of the potential difference is just the electric field times the displacement, the distance, capacitor spacing, if I'm dealing with a capacitor. And so, if the electric field went down, did the distance change? Did the capacitor spacing change? No. So what happens to the potential difference? It goes down. Yeah. So the potential difference goes down. If the potential difference goes down, I look at the equation for the capacitance. So by inserting a dielectric, I've reduced the electric field. And remember, I'm disconnected from the battery. If I'm connected from the battery, charge is going to flow to maintain the same potential difference across the capacitor. That's why I'm being very careful to say we disconnected from the battery. So the electric field's reduced, the electric potential difference across the plates gets reduced. So what happens to the capacitance? I've increased the capacitance of the capacitor. Which means if I was to reconnect this capacitor to a battery, what would happen? It would charge more. I've increased its capacity to store charge. Right? So that's how a lot of students, like when they first see it, is like, why do you want to reduce the electric field? Why do you want to reduce the electric potential? Now we can store more charge. Right?
Yeah. Makes sense. But what about, my dad kind of gave me a little bit of an overview of this when you mentioned changing epsilon, not epsilon naught, just epsilon.
Epsilon is when you take epsilon naught and combine it with kappa, I think. But that's not on the formula sheet.
Yeah.
So, thanks for making me look dumb.
Mr. Brand, you're so dumb.
I know.
Everyone point and laugh.
All right, so does that kind of make sense?
See, what happens whenever the students bully a teacher?
It's a good thing I have no feelings. All right, so can I erase all this?
I guess.
I'm recording, right? Yes.
Kappa is also some kind of Soviet missile.
That's the cap I've been referring to.
Yeah.
You
Soviet
wanna
missiles
fire
greater than
some
one.
into the electric field.
I'm pretty sure, I haven't thought about it for a while, but I'm pretty sure that's it. When you take epsilon naught and because the equation for on the formula sheet, the equation for capacitance is kappa epsilon naught A over D.
Yeah.
I'm sure kappa times epsilon naught is epsilon for that material.
Yeah.
Yeah, that's what he said. He was like, that can like, you can just write it as like a new epsilon.
Okay.
That might give you kappa times epsilon naught.
Okay, yeah. All right, so I want to go back to this. This is what I put up there whenever I was showing. Oh my gosh, where'd my brain go? Oh, it's right here.
Don't let your head.
So when deciding, and remember, you gotta remember when a capacitor is connected to a battery and you make modifications, charge can flow, potential difference remains the same. When you disconnect the battery, then the charge is locked in, but the potential difference can change, right? So you got to understand, based on the wording of the question, is the charge the constant thing or is the potential difference the constant thing? And then, so I like to say, and we've seen this already, but now we know what the dielectric constant, that's what kappa is, the dielectric constant. It's specific for certain materials, just like the coefficient of friction or something like that. So when deciding what will happen when altering a capacitor, I put this list up the other day to kind of help you out with the quest assignment. You know that according to the definition of charge density, the charge in a capacitor is just equal to sigma times the area. So you could say the induced charge on the top and bottom of the dielectric would be the induced charge density times the same area. We know the electric field. The total electric field for a capacitor is the electric field on the plates divided by the dielectric constant. So the electric field due to the plates would be the electric field that would exist without the dielectric. And that is going to be equal to, the electric field on the plate is sigma over epsilon naught. But now we have this extra kappa in there. And again, it would be sigma over epsilon if it was, before the College Board decided to. I'm sure it's probably easier that way, honestly. But the College Board. It's a good thing I'm not recording this and putting it on the internet.
Education monopoly.
We know that the capacitance is equal to the charge on the plate divided by the potential difference. The potential difference might change when I have the dielectric inserted, so the capacitance will change as we just showed. But it's defined in terms of the charge that's put on the plate, the actual charge that's delivered by the battery, not the charge that's induced. And on the formula sheet, we actually do have that's equal to kappa times epsilon naught A over D. Up until now, we've just had epsilon naught times the area over the plate separation distance D. But now we have it increases, right? By inserting a dielectric, we increase the capacitance. Again, we reduce the electric field, we reduce the voltage, but because the voltage and capacitance are inversely proportional, I've now increased the capacity to store charge.
That's why they call it kappa, because capacitor.
Exactly. Even though kappa starts with a K, but
English.
it sounds the same.
It's just like a spring starts with a K.
Yeah.
Yeah,
The K silent, like
exactly.
like nice.
Spring.
And then the energy stored on a capacitor is 1/2 Q delta V, which is equal to 1/2 C delta V squared. That's on the formula sheet. But remember, like we saw today, this can be Q squared over 2C. That's not on the formula sheet. And then our good friend that hopefully at this point you just have ingrained in your brain for a parallel plate capacitor, potential difference is electric field times the distance between the capacitor plates. If I have a dielectric in there, I get a new electric field that's modified by kappa. It's reduced by a factor kappa. And so the potential difference is also reduced by a factor of kappa. So these are the equations that you should have swimming around in your brain when you have questions about what happens to a capacitor when you do this or when you do that. Okay? Good times, right?
Correct.
All right, so let's watch some of this stuff happen. Let's watch the magic happen.
Just looking at that sweater.
What?
I get itchy just looking at the sweater.
I was horribly allergic to wool when I was a kid. Terrible. All right. So here I have a capacitor that I can now put some dielectrics in. And so I'm going to do kind of a similar thing. Where's my mouse? Similar thing. Get that up higher. No. Similar to what we did with the lab. Now this is the dielectric. I can now slide it in and out. And so my first one, I'm going to have a capacitor spacing. I'm going to start with the spacing it has now. I'm going to increase it to a potential of 1.5 volts by increasing the potential on the battery to 1.5 volts. And I can read the potential difference across the capacitor. And note here, I don't need to put the leads on the capacitor plates themselves, the leads on the voltmeter. As long as we're assuming no resistance in the wires, which resistance of wires is very small in comparison to the resistance of other circuit elements. We'll talk about that in our next unit. The resistance of this guy is, we can consider to be 0. So the potential, the electric potential from the positive terminal all the way over to the positive plate, the electric potential is the same. Okay, yes sir.
Does the voltometer affect
Voltmeter.
charge on the capacitor? Like when it's connected?
No, the voltmeter is designed to have essentially infinite resistance, so no current, no charge will flow through the voltmeter. Good question. Good question.
And how does that work? If it has no resistance.
We'll get into that when we study circuits. It's a good question too.
Beyond the scope of the capacitor.
Beyond the scope of this unit. I wouldn't say beyond the scope of this class,
Is
but
it magnetic?
analog voltmeters and ammeters that measure current, they definitely use electromagnetism. Yeah. Okay, and then everything on the negative terminal, everything here is 0 volts. Everything connected to the negative battery, to the negative plate, everything's at 0 volts. Everything here is at 1.5 volts. So the potential difference across the battery is 1.5 volts. Potential difference across the capacitor is 1.5 volts. I have a plate separation of 5 millimeters. I have a plate area of 100 millimeters squared. I'm going to charge the battery and then remove the battery. So now I've disconnected the battery. And then I'm going to increase the displacement to 10 millimeters. So I'm going to double the displacement, and let's see what happens to everything. I double the displacement. The capacitance went from 0.18 picofarads to 0.09 picofarads, which tells me that the capacitance was cut in half, which we expect because capacitance is inversely proportional to the distance. What happened to the plate charge? What happened to the plate charge? It's the red one there. This is the plate charge. It doesn't change. It's not connected to the battery. So Q itself is constant in this case. And the stored energy starts at 0.2 picojoules, ends up at 0.4 picojoules. Yeah, that's directly proportional. Notice that whenever you separate capacitor plates, you got to do work. And when you do work, you store more energy within the electric field that you create in the space between the capacitor plates. What happened to the potential difference? Well, let's look. It went from 1.5 volts to 3 volts. Why did that happen? Remember, you can always reference the equations.
And it has potential.
Electric field, what happened to the electric field? Stay the same. And we're assuming plate area is much bigger than distance between, so it's due only to charge density. Because the total charge didn't change, then the total charge density didn't change. So the electric field's the same, but we did double the distance, so we must get twice the electric potential. And if you just equate electric potential to electric potential energy per unit of charge, I've given those charges potential energy, just like you do when you lift an object up off the ground. I've given them potential energy by separating them, right? So that's easy. And notice the potential energy, stored energy gets doubled In this case, I disconnected the battery, so there's no more charge allowed to flow onto it, so the charge won't change. So as I increase the separation, delta V got doubled, and since the stored energy is 1/2 Q times delta V, this is different than the problem on the quest assignment, because the charge literally cannot change now. So this stays constant. We showed that delta V goes up by a factor of 2 if the D is increased by a factor of 2. So the stored energy will go up by a factor of 2 as well. So you see what I'm getting at when you, this is what the lab kind of got your feet wet with. These are the types of questions that you need to deal with when you're dealing with capacitors. And now we got the added complication of dielectrics. So let's talk about that now. So I'm going to start. I'm going to have a capacitor plate separation of 10 millimeters. I'm going to charge the capacitor to a potential difference of 1.5 volts. And I'm going to charge the capacitor, then remove the battery. And then I'm going to start here, insert the dielectric. And we want to see what happens to all the stuff. We want to see what happens to the charge, the electric field, the potential difference, the potential energy, and the capacitance. Let me list all those things. We want to see what happens to the charge, the total electric field, so the density of the electric field lines between the plates, the potential difference between the two plates, the total potential energy stored by the capacitor, and the capacitance. Hopefully, some of this we've already talked about, so hopefully it'll just kind of tie it all together. So let me reset everything. Bring up all my meters here. Look at the capacitance. There's nothing going on the capacitor, but I have capacitance. Right? It's there. I have capacitance. I want to look at the electric field lines. And let's say our dielectric is glass. The dielectric constant for glass is 4.7. So that means the total electric field within will be reduced by a factor of 4.7. The capacitance will be increased by a factor of 4.7. And notice, you might not be able to see, go on Google and just Google FET capacitor dielectric, and it'll pull this one up. It's not directly linked from their website anymore because they're converting to HTML or something. I don't know about computer stuff. But there's little positives and negatives superimposed on the little thing there. But when I put a little charge on the capacitor, I get positive at the top, negative in the bottom, the electric field lines. And then when I slide this guy in, those of you that are sitting up front, you see that what overlaid the positive and negatives get separated. You guys see that? If you can't see it, then I apologize. But just FET capacitor dielectric. Put that in Google and you'll pull this simulation up. And so whenever I slide that guy in, right, well, you can see it. Okay, sorry. Let me connect my voltmeter. So I've charged the capacitor. I will now disconnect the battery. I've charged the capacitor, so I have a lot of stored energy. I got plate charge. I got capacitance. I've disconnected the battery. Now I'm going to slide the dielectric inside. Immediately, what do you notice? I end with the same amount of charge on the plates, but what happens to the electric field lines? The electric field strength goes way down because the density of field lines goes down, right? And that should make sense. So when I do this, Q, there's no path for charge to flow onto or away from the capacitor plates, so Q is unchanged. The electric field has been reduced. And if I was to count those field lines, it's been reduced by approximately 4.7 times, right? You divide the total electric field, or the original electric field, by 4.7, that's what you're left with. So the electric field is reduced by a factor kappa. What do you think the potential difference? What do you think is going to happen to the potential difference? It goes up? Goes down. Look, I put more in here. I put the dielectric in there. The electric field has gone down. If the electric field goes down, then the electric potential difference must also go down. Right? And notice that with the charge separation within the dielectric, the potential energy between the top and bottom plates isn't as much because it's essentially being partially neutralized. Right? So you can think of it that way, or you just think in terms of the equation. So yeah, the potential difference is also reduced by a factor of kappa. And because electric potential energy is directly proportional to electric potential difference, the stored energy also goes down by the same amount. Right? Or you can look at the equation for stored energy is 1/2 Q delta V. I mean, we just talked about this, but just to drive it home with a visual. Charge stays the same. You can't change the charge. It's not connected to a battery, so the potential goes down, as we already showed. So the potential energy must go down by the same factor. And you can also look at the definition for electric potential energy. Electric potential is just potential energy per unit of charge. So they're directly proportional. So you can think of it that way as well. And then the capacitance. So this is the same thing. All these. The capacitance, though, because it's inversely proportional to the potential difference, then it will be increased by that same factor. All right. I got a couple more examples of this for tomorrow, and then we'll start on a quest assignment. It'll be a shorter one, just dealing with dielectrics.
Will we do something where the dielectric is not the same as B? There's just like a thick sheet of glass between the two, but it's like in the middle?
You could, yeah.
Would that have the same result as that, or would that be different?
We'll talk about that later. Maybe tomorrow. Good question.